All right, this is DES Part 2. And I put the last year's recording of DES up there. So let's continue on. Okay? All right. DES stands for Data Encryption Standard. Okay? They submitted the Lucifer cipher. Do y'all remember what the name was? I actually updated on the slides last semester.
Demonstration.
Right, it was demon. Everyone thought that was for devil. It was actually for demonstration, but they were limited in length of characters, so that's why demonstration became demon, which people thought was the devil, which was Lucifer, and it's like that's actually a question somewhere, either a bonus question or a test question or something. It is one of them. I don't remember if it's a test question or bonus question, but it's something. Okay, so they submitted it in 1974. Okay, the original algorithm uses 48 to 128 bits. Okay, that's kind of weird. They had something that was variable bits. Or variable block size, basically, 48 to 128. They chose 64 bits. Why? That's what a lot of people think. It was too hard to crack. And if you read the book Crypto by Stephen Levy, they talk about PGP. And the book's awesome. It's called Crypto by Stephen Levy. You can buy it for under $5, including shipping. Okay? They talked about when PGP came out. They were pissed. And when PGP2 came out, the NSA specifically told them, do not release this code no matter what. And he said, okay, I'm not going to release it. He just stuck it on a bulletin board, though. And everybody else released it. So, but it got to the point where NSA says, we can't break this. It's like LastPass and the stuff I use to store my passwords encrypted with AES, and they tell you, if you lose your password, don't come crying to us, because you ain't getting it. Now, you're losing your stuff, okay? So they decided on a 64-bit version. Okay, it says the 56 bits make up the true key, and 8 bits are actually used for parity. So it's really a 56-bit key, but 8 bits that are used for parity, which is more like error-checking information, if you kind of think about it. Okay, Lucifer was altered, become the data encryption algorithm, which was DES. Okay, all right. So far, so good. All right, it says NIST. I actually read an article today that due to the government shutdown, NIST has not been able to update a standard that was due on the 12th. And it's like, oh, great. So I was actually at NIST, 3 weeks ago? When was I in Maryland? Just recently.
2 or 3 weeks ago.
Yeah. And they were talking about having to have it updated by October 12th, and it shouldn't be a problem, and they didn't do it. So I'm glad I was there before they closed it down, because it's a nice place. Okay. So they determined the need to protect sensitive data during the 1960s. What were y'all doing in the 1960s? Being born. I was born in 62. I wasn't thinking much about computer security in 1962. Yeah. What were you doing?
Fighting bears.
Fighting bears. Okay. It says they implemented a cryptography program in the early 1970s. Computers are starting to get popular out there. We need to do something about it. Okay. They invited vendors to submit techniques. Okay, IBM was developing one for financial data back at that point. Then they submitted Lucifer, and it was accepted. Okay, this is controversy over if NSA requested it to be weakened. Again, we still don't know that one. No one seems to want to tell us the answer to that one. Right? So, but it was one of the original ones. But it's kind of like Microsoft code, a secret code originally. When it was originally put out there, we didn't know what it did. It's that whole open source versus off the shelf versus an open source. Which one's better? That kind of thing. Okay. All right. Became a national standard in 1977, and an ANSI standard in 1978. Okay. How big was the internet in 1978?
Not that big.
Like 3 computers. Okay.
It was everywhere.
I was talking to the students yesterday about 1990. I was over in the Persian Gulf War when a software program got infected with a virus and needed to be fixed. And it was going to take 2 weeks for the military to get the guy that wrote it to Saudi Arabia. Had no internet, had no way to get it there in 1990, so they literally were flying the guy from Tinker Air Force Base to Saudi Arabia to fix the program. So I fixed it for him before, in the next couple of days, but still the point was, there was no internet back then, there was no cell phones, there was no nothing, yet they're thinking about this stuff, which is kind of, it always amazes me I think back to the Caesar cipher. I'm thinking short skirts or on everybody. And what do they got? Chariots and swords. And someone's actually thinking about secret data. That's kind of cool, though. They're actually thinking about that kind of stuff. And how about Kaczynski? What, 1878? Was that Kaczynski? Okay, maybe 1876. And the dudes think about a way to break the veneer cipher. That's way beyond me. So, all right. So it's designed and implemented in a majority of commercial products requiring cryptography and in almost all government agencies. Okay. It was tested and approved as one of the strongest and most efficient cryptographic algorithms. So what do we think about it today?
Oh, it's perfect.
But still, you know, back then it was amazing. You know, we look at the stuff we have today. Like I was reading an article about the 20 things we don't have. And, you know, the technologies that are available we haven't implemented. This guy made this extension cord that looks like a roll of duct tape. You literally roll it out across the floor. It's totally flat. And you can put it on the carpets, and it's like, why didn't we ever think of something like that? It literally was flat, just like a piece of tape. And it's like, but back then, you know, we're developing this stuff, and again, we didn't know what was even needed at that point. All right, now let's talk about it. DES, a block symmetric algorithm. What does block mean? Okay, we work in chunks of data. Okay, if we're encrypting 64 bits at a time, but we got Kenny over there typing 1 character per hour, we're going to wait until we get a whole block before we do something. That's a block cipher. Stream cipher would be as you enter something, we're encrypting it on the fly, 1 character at a time. Okay, it's symmetric. What does symmetric mean? Same key, symmetric, same key. Quite a few people miss that on the test. They might have missed it because they couldn't read the question. I'm not sure. But some of them missed it. Okay. Okay, since blocks of 64 bits are put through 16 rounds of transposition and substitution ciphers, order and type of functions are dictated by the key value. Okay. Again, we only walk through 1 time, but it really goes through 16 times. Since for government agencies, it's used to protect sensitive by unclassified data. Okay, hopefully you all know the data classifications. All right, now let's talk about some of the block modes. We're only going to talk about one of them today, bro. About 2 of them. Okay. There's one called electronic code book, and I will tell you, the block modes, you need to know them. If I give you a picture and say, what is it? Just so you know. Okay. Electronic code book modes. The same ciphertext is always produced from the same plaintext. What that means is, if I take some plaintext and run it through an ACB mode of DES, we always get the same ciphertext, okay? So I always start with the same plain, I always get the same cipher. Is that good or bad?
Bad.
That's actually bad, yes. Okay. It's easier to identify patterns, okay? It's best when using a small amount of data. It says each key indicates a different code block. It says uses message authentication for integrity and authentication. And here's the picture of it, okay? So we got our plain text going through our cipher with our key, and we get our ciphertext. They're not linked together in any fashion. So we put some plain text here. If we run the same plain text through, we're always going to get the same result. Okay? Everybody see that? They're not chained together in any way. Okay? All right. Now let's talk about Cipher Block Chaining, CBC. So for that one there, for electronic code book, remember, same plain text, same ciphertext every time. Okay. So on CBC, this is encryption is dependent on variables from the previous encrypted block. Okay. This is encrypt 64-bit blocks. You can't see the end there. It's a T. 64-bit blocks, but chains them together by XORing each ciphertext blocks with the next plaintext block before encryption. Whew. Let's see what that does. So we take some initial value in our plain text, okay? So we take our plain text, some initial value, XOR them together. Y'all remember what XOR was? One or the other, but not both? Okay? We're going to go through a whole bunch more of that soon. Okay? So we take the initialization vector and the plain text, XOR them together. We encrypt that, okay? The results of that becomes our ciphertext. Okay? that ciphertext becomes the next initialization vector. Okay? So the results of the first encryption is actually the initialization vector for the second one. So if I put the same plaintext in each places, all three places, will I end up with the same ciphertext? No, you will not. Because remember, the first one's XORed with the initialization vector. The second one is XORed with the first ciphertext. The third one is XORed with the second ciphertext, and so on and so forth. To decrypt them, you took the first ciphertext, decrypted it, then XORed the result with an initialization vector, and then so on and so forth. The next plaintext was XORed afterwards. So now they're linked together. So now it's more random. If I was to take the same plaintext on the first one, ECB, they're all the same. If I took the same plaintext here, it's going to be very different. Okay? Ever see that?
Does that just go 3 steps, or does it?
Oh, it can keep going forever.
What stops it?
You run out of data.
Okay.
Yeah,
Is that per block then?
yeah, this is the block.
Okay.
Now, this is one 64-bit block here. Okay?
My apologies.
Yeah, no problem.
I have a
All right.
question.
Okay, go ahead.
The first XOR.
Let me go back. Okay? Right here. First
yes.
XOR, top.
What data do you use for that XOR?
We use some sort of initialization vector. Like some places we're talking about using something like U.S. Army HQ. Is that a good thing? Not necessarily. But a lot of places did it. But normally you'd want a random initialization vector.
So it'd be given.
Right. Just some random string to start with. Okay? But a lot of places would start with something like U.S. Army HQ. But the bad thing with that is that I know what this initialization vector is. You know, I mean, anything that's a preset value is a bad thing. It's just it. So, yeah, that would be given. It's the same thing that's used to decrypt. It's like the plaintext, it's a key, basically. All right? Okay. Let me stop this one.